Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Sustainable Water Futures. My name is Daniel McLean, and I'll be your host today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the land and country throughout Australia and recognises their continuing connection to land, waters, and community. We respect and pay our respects to them and their cultures and to elders, past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Queensland University of Technology. The QUT Faculty of Engineering is shaping the future by tackling global challenges like climate change, environmental sustainability, and population ageing through cutting-edge education and research. They offer students transformative, real-world learning experiences and work closely with industry partners to drive innovation and create lasting impact. With a strong focus on sustainability, inclusion, and Indigenous engagement, they are preparing the next generation of engineers to lead with purpose and make a difference in their communities and beyond. Today we will hear from two speakers, followed by our live audience Q&A. And I encourage you to send through questions to our speakers via the chat box. I'd now like to welcome our first speaker, Dr. Yang Liu. So Dr. Liu is a professor and chair of Sustainable Water Technologies at QUT, ARC Future Fellow, and director of the newly established ARC Research Hub for IoT and Water. She joined QUT in 2023 after serving as a professor for 15 years at the University of Alberta, where she held the prestigious Tier 1 Canada Research Chair and NSERC Industrial Research Chair in Sustainable Urban Water Development. Her research integrates microbial ecology, bioreactor design, and systems engineering to develop energy efficient, climate resilient, and wastewater solutions, with a focus on circular nitrogen management, resource recovery, and real-world implementation with industry partners. I'd also like to welcome our second speaker, Dr. David Bergman. Dr. David Bergman is the CEO of Water Research Australia, a member-based organisation comprising of water utilities, council operators, regulators, universities, consultants, and suppliers. They broker and deliver research on their behalf. He has a PhD in chemistry and has worked in R&D roles in chemicals, food, and now water and wastewater sectors from global multinationals through to regional utilities. David is passionate and active in areas such as resource recovery, green chemistry transformations, alternative water strategies, cooling and livability, and real-time monitoring and control through IoT. Please welcome Dr. David Bergman and Dr. Yang Liu.
Thank you very much for the introduction. We're here today to explore how we can reimagine wastewater as a valuable resource that can support more sustainable and resilient water future. So if we look at our conventional approach to sanitation, especially in urban areas, wastewater is collected from each individual household and transported through extensive underground piping networks to centralized treatment systems. And after treatment, the effluent is typically discharged into nearby water bodies. These type of systems are largely based on 50 to 100-year-old designs. They're very energy intensive. The sector accounts for about 1 to 5% of the total electricity consumption in many countries and emits significant greenhouse gases. Also, at the core of the design is the assumption that excreta and wastewater are wastes, and therefore wastes should be disposed of. And there's very limited consideration in terms of resource recovery from wastewater. This type of linear and disposal-oriented model is not very sustainable. There's an urgent need to rethink and redesign how we can better manage wastewater. I will now pass it over to David.
Thank you, Yang, and welcome everyone, and thank you for the opportunity. So in understanding really where we need to go in terms of developing sustainable water futures and systems, it's important we take the opportunity to just zoom out a little bit and look at some of the key drivers and trends happening in the water industry. And potentially those listening in might see these as being pretty common to their industries as well if they're outside the water sector. So there's really three key trends, and we could debate if there's more as well or whether these are exactly the right ones. But for the purpose of today, there's really three main trends impacting the water sector, that of population growth and urbanisation, and we'll unpack these just a little bit more in the coming slides. Climate change and also ageing infrastructure, and you can see those at the centre of the diagram. Around that are a lot of the impacts or the disruptors that are happening, and these are perhaps shorter term impacts that are having an effect on the industry that we still do need to deal with and cope with and manage through, but at the heart of those trends and drivers that are there for sustained periods of time. So we'll briefly unpack a couple of those at the middle. That being of population growth and urbanisation first. Here's an image of the eastern suburbs of Melbourne, courtesy of Monash University, showing development from 1985 through to 2020. Now I'm going to put a second image up on the screen as well, which is the western suburbs of Melbourne. So take a look at one at a time. You go a bit cross-eyed trying to look at both, but you can see the rapid rate of development of Melbourne, and this would account for most urban centres across Australia. We're moving from open, in a lot of cases, either forest or farmland, replacing those natural environments, natural waterways, natural runoff with hard surfaces, roads, houses, reflective surfaces, creating all sorts of changes to the environment relative to its original pre-development status. And that creates all sorts of pressures on a water utility, obviously to keep up with growth with those assets as well. Pressures on the community are there as well in terms of traffic, their own affordability, but then also well-being in terms of the greening of the environment or lack of greening, as well as urban heat island effect, some of the health issues that can come with that. The second trend or driver of change is around climate change. So if you're in the southern states of Australia, despite some recent rains, you're perhaps experiencing some of the lowest rainfall, or certainly very low below average rainfall for the last 18 months, even closer to 2 years. If you're in some of the northern states, you're experiencing a number of floods in recent times and higher than average rainfall, including cyclones. For those that recall the early 2020s, where we had this succession of extreme events from drought, bushfires, floods, followed by more floods. And so these events are becoming more extreme, again, placing pressure on the water sector and water utilities, how to plan for these kind of events, how to make their infrastructure more resilient to these impacts as well, and just manage the costs of planning around that. The third trend or driver for change is around ageing infrastructure. So here's a chart courtesy of Southeast Water in metropolitan Melbourne, just showing the age of assets. Really, from the 1950s, the growth of Melbourne really exploded. So as a result, a lot of those assets are now significant proportion of them approaching 70 plus years. And so they need to be dealt with. That creates cost pressures on the water utilities, creates affordability issues for the customers in those areas. And also when they fail without good warning, it leads to customer dissatisfaction about the level of service from their water utilities. So part of what we're presenting today is how a water utility needs to shift from this quite linear progression of from catchment through to pipes and pumps, distribution, treatment, and ultimately outfall, a very linear sequence, to one that is much more sustainable, one that is more circular, one that taps into and recovers resources for it, one that is more energy efficient, lower emissions, and just more adaptive and resilient to the community, the environment, and the climate that we are in. And we'll progressively unpack that. What does the future water utility, a sustainable water utility, look like? And this is where I pass back to you, Yang.
There are many ways to think about sustainable wastewater management. So David and I have summarized our journey towards sustainability into 3 key elements that we believe are essential. The first is around low carbon, focusing on cutting emission and designing systems that use less energy and even produce energy. The second is around the circularity. That's when we start to shift how we think about wastewater, looking at how we can recover useful resources like water, nutrients, materials, and energy from wastewater. And the third element is around making our system more adaptive and building systems that can handle climate impacts and meet the needs for different communities. So we'll follow the 3 elements to get our discussion on what rethinking wastewater management could look like for our water industry. Because we'll be talking about how we might improve our current wastewater treatment systems, we thought it would be very helpful to first give a quick overview of our conventional sewage treatment systems. So basically, we have 4 key processes. So the treatment starts with the solid removal in primary settling, followed by the activated sludge process as the second step, where microorganisms use oxygen for organics and nutrient removal. And then we have the secondary settling for removal of remaining solids. The sludge can then be managed in the 4th step with a process like anaerobic digestion, where we can recover some energy. But not all wastewater treatment plant has an anaerobic digestion process. So we'll start with the first pillar. Back to you, David.
So as we take our transition down the journey to be a sustainable water system in a low carbon future, let's look at first the emissions that are coming from our wastewater system. It's important we look at there first. Those are those scope 1 emissions. Those are those ones that we can hopefully monitor and control and mitigate as part of a wastewater treatment process. And those significant emissions can be significant. It's important that we have good monitoring in place, that we understand the emission hot spots from treatment processes, and then put those strategies in place. So, for example, nitrous oxide emissions are significant and are often underreported or underrepresented within emissions factors or emissions modelling. And there's research emerging in this space. Nitrous oxide gases, a greenhouse gas 300 times more potent than traditional greenhouse gases, are of concern and something we need to be monitoring and tracking carefully, which leads to a particular global project that is underway. Wastewater emissions from wastewater treatment plants is a global issue. They are across the globe. And so there's a global project that is focusing in on making sure we monitor nitrous oxide emissions across the plant. We know exactly where those emissions have come from. We establish best practice in this space so that we are able to compare and share and build the knowledge in this space. So ultimately, the mitigation actions that we put in place are going to make a difference, are going to help us meet our climate change and net zero goals. Back to you, Yang.
So with the low carbon concept, another very important consideration is to reduce energy use. We mentioned earlier that wastewater treatment systems are very energy intensive, and this graph shows how that energy is distributed. As we can see here, aeration process uses majority of the energy, and this energy is mainly used to remove 2 key pollutants, the organic matter and the nitrogen. However, organics are also the potential energy source, and we can actually design our system to capture them. But in terms of ammonia, currently there are still challenges to directly recover ammonia from mainstream wastewater. So we should really consider how we can reduce energy demand for ammonia removal. At the sewage treatment plant, ammonia is normally removed through a process called nitrification denitrification. This process begins with ammonia being oxidized to nitrite and then to nitrate. And in the final stage, nitrate is then converted to nitrogen gas. So this process involves three main groups of microorganisms: ammonia oxidizing bacteria, we call AOB, and nitrite oxidizing bacteria, or NOB, and denitrifying bacteria that carry out the rest of the reduction reaction. So normally, NOB would outgrow AOB, and therefore, as soon as the step one, ammonia oxidation, is carried out, nitrite can then be quickly converted to nitrate. So the first step consumes around 75% of the total oxygen demand, and the second step consumes about 25% of oxygen. And the nitrate reduction process does not require oxygen. So there are two key opportunities for us to consider to reduce energy consumption for ammonia removal. One is the direct optimization of the treatment process, and the second is around manipulating reactor microbiome community and develop more energy efficient biodegradation pathway for ammonia removal. As an example, started in 2010, we conducted this 3-year study at a full-scale sewage treatment plant. Our objective was to explore how we can optimize the treatment process and save aeration energy. So we conducted sampling at 9 locations throughout the biological treatment process. Follow the flow path. So we have first anoxic tank, the anaerobic tank, the second anoxic tank, and then 3 aerobic tanks. So we sampled at the beginning, at the end of each tank, and monitored the removal of COD, ammonia, phosphorus, metal, and other pollutants, as well as the microbial community dynamics across different seasonal and flow conditions. So we observed, for instance, during the low flow or summer conditions, COD and ammonia can both be fully removed after the first aeration zone. This basically indicates that under these conditions, we can reduce aeration in the aeration tank. So in our study, we largely focused on when and where aeration can be safely reduced without compromising the microbial activities, the stability, as well as the treatment performance. So with this study, we were able to develop this targeted aeration strategy, which has led to the average energy saving of around 10%. And this is exactly the type of low-hanging fruit we should be looking for. But if we want to further improve the energy efficiency for ammonia removal, we'll need to rethink about the microbiology themselves. So again, if we look at the conventional nitrification denitrification process for ammonia removal, what if we can inhibit the growth of NOB, the nitrite oxidizing bacteria? That basically means that nitrite produced by AOB in the first step can be directly utilized by denitrifiers and converted to nitrogen gas. So this process is called shortcut nitrification, and this can save up to 25% of oxygen demand. Now, if we can introduce a new group of microorganisms called anaerobic bacteria, which are capable of converting ammonia and nitrite directly into nitrogen gas without oxygen, we can save even more energy. So this process is called partial nitrification and anaerobics, or PNA. So in this pathway, about half of ammonia is first oxidized to nitrite using oxygen, and then the rest ammonia is then removed with nitrite by anaerobic bacteria. A variation of this process is called PDA, which can achieve similar outcome. So overall, with PNA and PDA process, we can achieve about 50 to 60% reduction in the oxygen demand. And therefore, by selecting and encouraging the right microbial consortia, especially AOB and anaerobic bacteria in the reactor, we can significantly reduce aeration energy. But the question is how we can actually achieve that. So if we look at this table, this basically highlights some of the ecological characteristics of the three main groups of microorganisms involved in the biological nutrient removal. So AOB, NOB, and anaerobics. It turns out that these microbes differ in several different or important ways. For instance, for their growth strategy, AOB like more dynamic and changing environments, and NOB prefer more stable conditions. And their oxygen requirements, stress tolerance, preferred pH range, and sensitivity to inhibitors like free ammonia, all very different. So this type of differences give us an ecological lever that we can use to select the target microbial community. So the next step is, of course, to apply the knowledge in practice. And this slide shows some of the bioreactors we operate in our water innovation lab at QUT. We call it WISE Lab. So in order to select the desired microbial consortia, we often run multiple bioreactors in parallel, and each with slightly different conditions like dissolved oxygen levels, aeration cycle, or feeding strategies. Then we would compare the microbial community and their activities that develop in each system. And the goal is really to link the microbial behavior and their ecology to engineering design and control strategies. This approach can help us to develop more targeted and energy efficient and robust treatment solutions. One process we developed in our lab is called this granular sludge reactor. We call it GSR technology. This is based on the shortcut nitrification process. So the GSR process is designed to treat high ammonia wastewater and can achieve over 5 times higher nitrogen loading capacity compared to conventional systems. We have already demonstrated this process for for the treatment of a range of high ammonia wastewater types, including centrate, landfill leachate wastewaters, and other industry wastewaters. And in our lab, we're also been working on other nitrogen removal pathways. One process I'm showing here is called sulfur MOX. So it's sulfate-dependent ammonia oxidation. This pathway directly couples the oxidation of ammonia with sulfate reduction, producing nitrogen gas. So this sulfur MOX also often coexist with other processes like anaerobic heterotrophic sulfate reduction and sulfur-based autotrophic denitrification. So this process does not really require any energy. So we're saving about really 100% of oxygen. But the major challenge in here is that these are very slow-growing microorganisms, and the reaction is very slow. So in my lab, our focus has been around optimizing the system with ultimate goal for scaling up for this process for practical use. So now I would hand over to David to continue the discussion on resource recovery.
Thank you, Yang. So as we continue our journey towards a sustainable wastewater future, the second element that we've outlined is for the water sector, water utilities to be more circular in their approach. In particular, focus on their approach to resource recovery. And there's 4 elements to that we'll move through here as it applies to wastewater and what can be recovered. There's nutrients to be had there's other materials to be recovered, there's the water itself, obviously, to be taken, and then there's the energy, and we'll move through those. The first 2 that I will focus on next will be around the nutrients to recover and also to the carbon side of it or other material elements to it. So this is where a water utility or a wastewater system needs to really move away from thinking of itself as a linear operation, wastewater in, treated a product out for disposal. It needs to see itself participating in a circular economy, and a circular economy almost being like layers of an onion. It can be quite a small circular economy focused to a part of a plant, or the whole plant, or even a circular economy outside of its boundaries associated with the industry around us. And we'll unpack a few of these, particularly here around what are some of the green chemistry transformations that are possible for the resources recovered. We'll touch on cellulose recovery and its transformations and possibilities. We'll talk about the sludge or the biosolids that's collected at the end of a wastewater process and the kind of carbon products that can be used for. Also, we'll briefly touch on algae and some other options as well. So here's another possible configuration of a wastewater treatment plant, slightly more complicated than the one that Yang put up earlier, but there's ways we really need to look and break down the process. What is there that can be recovered at the beginning of a wastewater process? So, for example, there is emerging technology that's showing that the cellulose is recoverable from wastewater treatment. So the cellulose predominantly from the toilet paper that's used in our sewage system. Also focusing in at that digester stage, there are materials that can be produced that can feed and create proteins that could end up in possible feedstocks, volatile fatty acids that could be created to produce other chemicals and bioplastics, for example. Or we could be optimizing and harvesting the biogas and biomethane coming from that, or really focusing in on the carbon and the type of carbon products. Plus the opportunity to really participate in that wider circular economy by looking at what are the other food wastes or organic wastes that can be brought in to a treatment process to feed it effectively and create more value out of these pathways that we're establishing here. So we'll look at a few more of these. Firstly, that solid product that remains at the end of a treatment process, some call it sludge or biosolids at various levels of dryness. And there's those solids remaining. Traditionally, a wastewater operator may have come up with an arrangement with agriculture, nearby farmlands to distribute it to land. And it does have great carbon, nutrient, nitrogen, phosphorus value and is very effective. These days, with the number of emerging contaminants that are coming through in our wastewater systems, so just think PFAS as one particular example, that's becoming an increasingly unviable option to be sending that to land. So the industry is really looking at, in particular, thermal processes to convert these biosolids, rich in carbon, nitrogen, phosphorus, and other things, into materials of value, carbon materials of value. And pyrolysis is getting a lot of consideration at the moment in Australia and other parts of the world. And so that is the kind of thermal process, different levels of temperature to favour a carbon type output at the end of the day. Carbon being used in a whole bunch of areas, batteries, electronics, purification, even water and air purification as well. I'll come back to some other pathways and possible products from these processes as well. I just wanted to touch on the principles of green chemistry, particularly as I'll talk about cellulose in a second. Cellulose being an interesting feedstock that can lead itself into these kind of transformations to produce other chemicals, platform chemicals, bioplastics, for example. And it's been established for some time now, the 12 principles of green chemistry, of which I'm not going to go through all of them, but the water sector has a great opportunity to design and really consider what they do, in particular, taking the endless source of carbon feedstocks coming through the wastewater system and other elements as well that are possible there, and taking the opportunity to, rather than just destroy or destruct or dispose, to actually try and keep some of these materials at their highest possible value and convert them into other materials of value, and really look at the way green chemistry can help in those processes. And there's been a lot of thinking done on this already. We don't need to reinvent the wheel here. So if we're able to isolate, for example, cellulose or other materials out of our wastewater systems, there's an enormous number of possible pathways to convert these materials into other materials of value, reducing our reliance on non-renewable feedstocks or petroleum-based, and actually replace those and use those for a much more sustainable future. So let me briefly touch on cellulose. The technology is emerging for us to recover cellulose from the front of wastewater treatment plants. That cellulose can either be used directly in other products, so roadways or other construction, for example, or even in other packaging materials, derivatized to produce much more sustainable packaging as an outcome. Also, too, by removing that cellulose, there's research and reports emerging that it has the potential to increase capacity of our wastewater plants, obviously reduce their energy demand and their carbon emissions as a result, and lead to much more efficient processes, aeration savings, sludge reductions. So what do you do with that volume as well? So it's an emerging field where much more research potential here, and a lot more to do, and a lot more renewable or green chemistry outcomes possible. So in terms, we're not making this up, but these kind of green chemistry transformations from cellulose are happening in other industries as well. This is an example where they're particularly taking sawdust. So it's not a wastewater example, but it's being converted into a much more green chemistry-based solvent for further chemical transformations, and is proving that cellulose is a feedstock from other sources of biomass, and there's no reason why we can't be applying that to the biomass we have in our wastewater to produce much more sustainable outcomes for the water sector and for the chemical and bioplastics and polymers industry as well. Said I would come back to other outcomes other than carbon, in terms of there's other thermal transformation processes to be applied to sludge or biosolids. In this case, it doesn't require the product to be dried as much, which is an energy saving in itself. And by using pressure, lower temperatures are required, using supercritical properties of water under pressure to become an excellent solvent, and favour a process that is more towards biomethane, and also then products that are low carbon products with the inorganic nutrients to potentially lead to pathways for agriculture. So it just represents an alternative pathway from carbon to a carbon product like biochar to biomethane and nutrients, depending on the context or the situation or the economics of the particular situation for a water treatment plant and their pathway to a more sustainable future. Algae is also emerging field where algae, in particular macroalgae, is proving to have a number of benefits. Where the algae is being used, algae is great because it's a photosynthetic process. It's using sunlight, natural energy from the sunlight, it's consuming CO2, it's producing oxygen, it's drawing down that CO2 in the carbon to produce a biomass, which then can be further transformed into other things. It's also taking the nutrients up as well to produce a very naturally produced, much cleaner water system as well. And then opportunities for what can be done with those nutrients and with that biomass and the other potential green chemistry transformations that are possible. Having said that, there are some warnings in some of these transformations to more sustainable solutions. We still need, and there is a lot of research going on, but more to be done to understand the fate and the outcomes of a lot of the contaminants that might be present. So thinking PFAS is one of those examples, heavy metals, for example, example, pharmaceuticals and cosmetics, to making sure that these are being dealt with properly. So as we pass them on in the circular economy, we're not passing problems further into the food chain or the environment in what we do. Also, too, we should be considering the origins of the wastewater and our opportunities to actually recover nutrients and resources of value at the beginning of the process, not just be focused on our treatment plants and what can be done there. So here's an example of an innovation and technology being developed by UTS, Southeast Water, and other partners. We're using a urine diverting toilet. They have created a mobile public toilet, which they plan to use to test the technology and also test community and customer acceptance of this kind of circular economy, where the urine is taken using biomembrane technology, converted into a liquid fertilizer. As a result, there is less nitrogen entering the wastewater system and hitting our treatment plants, leading to less aeration needs, more efficient processes, and of course, helping mitigate the potential for nitrous oxide emissions. So we'll keep moving on in our journey of resource recovery, and we're going to look at one of the more important parts and why we are here in many ways, looking at water reclamation and reuse. Been very focused on the topic, but it's very much important that we look to save every last drop in our world of climate change, water scarcity, and water security. So here's on screen is an example of a great piece of work put together by WASA, the Water Services Association of Australia, where they have, with their partners, been mapping out globally the various reuse and reclamation schemes where water is being reclaimed from wastewater and other sources and being reused. There has been, perhaps understandably, some hesitation in Australia to adopt this, some concerns and community acceptance about it. But here we can actually say there's a lot we can learn globally. There's a lot going on globally in this space. Plus, there is a lot more planned here, and there's a lot more possible. So there's a good reason for us to do it. In Australia, our sources of water are currently very rainfall dependent. We should look at it more. We're resurface water dependent, and by that we mean water that's in our catchments, in our lakes, and in our rivers. And of course, in times of drought and low rainfall, we are very susceptible to that. And it's also our most climate susceptible source of water. So we really do need to be looking at all options of water that are possible for us, which is exactly the name of the title that WASA put together. All Options on the Table was a report back in 2020. And the numbers may have moved slightly in this time, but I think the message is still there, that surface water is, you can see it's in terms of the yield or what's available to us, it does have its limits, and particularly in terms of dry years, climate impacted years, that can be a problem. So looking further at the other possible solutions, such as desalination to the far left, or recycled wastewater, provide us much more larger sources or yields of water as sources of supply for a much more secure water supply and sustainable water supply in Australia. As part of that report, they all looked at expected costs for those kind of solutions. And yes, recycled water and desalinated water is more expensive than current practices. But in a climate changing world, in extreme events, in years of water scarcity, you begin to bring in some of those costs on the far right-hand side of things if we haven't planned in advance, if we haven't planned around how we use our recycled water, how we're recovering our water from our wastewater and using desalination to keep our water supplies high, then suddenly we find ourselves in a very costly scenario. So the time is right now that we are adopting these wastewater recovery practices, water reuse and reclamation, now to secure our supplies and be a much more sustainable water system and water utilities. A couple of things to support that are going on in the industry and are needed in this space. So in order to recover wastewater and reuse it, it's important, and it's surprising this doesn't exist. There are no standard protocols for validating the treatment plants, treatment processes associated with this. So we are working together with global partners to establish these standardized treatment protocols so that water treatment operators can claim all the possible log reductions and chemical contaminant removal steps that are possible. That leads to more efficient operations that are cheaper to run, cheaper to design, cheaper to build. So saving significant costs and meaning much more efficient operations by having validated and treatment processes. Also, to building our resilience to drought. So by using highly treated recycled water to keep our catchments and our dams at very high levels. If we look back at learnings and research from the Millennium Drought, environmental flows were cut to make sure that our cities had enough water in them, which in the hierarchy of needs was important. But I think there's a learning there that it's important that our environment was permanently damaged in some places as a result of that. The rainfall runoff relationships that existed pre-millennium drought no longer exist. So it's important that next time we experience these times of extreme water deficiencies, we are able to look after the environment as well and be more sustainable and long-term. Also, too, as we face more extreme events, our water supply catchments, as happened in the early 2020s, experienced after drought and bushfire some pretty significant events hitting the catchments. And so if we design for a peak event such as that hitting, we will be making some very costly solutions. But if we're able to use some good modeling and actually understand the volume that we can use through these events, where's the good quality in our catchments, and basically await for the treatment system and the water supply to be consistent, and then we treat for that. Wait for full mixing, and then we treat to that level rather than treating for the hotspots in these systems, saving us money and being a much more sustainable solution in the end. Also, too, if we are to be using more sources of water, it's important that we understand, and we are studying in this space, the source of these waters, monitoring them more closely and how to do that more efficiency, and then controlling them. And this is where we're looking to make the most of some protocols established in North America to really better understand the sources of these wastewater and hence how we can treat them more efficiently and more effectively. Also, too, it's important in wastewater treatment processes that disinfection and advanced oxidation processes are happening to remove those particularly carbon-based contaminants. But as we are studying and continuing to study, it's important that we don't also produce harmful disinfection byproducts as a result of that, and get the right treatment processes, advanced oxidation processes, to be both efficient and also safe to do. So now this is where I pass back to Yang. Over to you.
Thank you, David. Just to continue on the topic of resource recovery, there are actually quite a few different opportunities we can consider for recovering energy from wastewater. But in here, I will focus mainly on the biogas recovery, and this is one of the most mature and scalable methods currently available. So biogas recovery is primarily linked to organic matter in wastewater. In conventional sewage treatment, organics are removed using activate sludge process, and this requires large amount of oxygen to convert organics to CO2, and this is a net energy consuming process. Alternatively, we can design process like anaerobic digestion, which converts organics into biogas. And this biogas can then be used to generate electricity and heat, and this process does not need oxygen. So let's take a closer look of how the organics are typically managed in conventional sewage treatment plant. One point to mention here is that in wastewater field, we typically use COD, or the chemical oxygen demand, as a measure for organic matter in wastewater. So we start with 100% of COD in the raw influent. Out of this, about 10% typically remain in the treated effluent, meaning that they cannot be removed. But with primary settling, we can remove about 40% of the COD that is captured in the form of primary sludge, and then another 20% of COD ends up in the form of secondary sludge. That leaves about 30% of the COD being oxidized to CO2, and that removal of this 30% of COD, of course, requires significant energy input for aeration. So in the sewage treatment plant that has anaerobic digestion process, then we can recover around 33% of the COD from the sludge as a biogas, and the biogas can then be used to generate heat and electricity. What we can see in here is that the more COD we can divert into the sludge, the more energy we can potentially recover through anaerobic digestion. And therefore, if we want to capture more COD in the sludge, one approach is to conduct this chemically enhanced primary treatment. So we add an additional chemical dosing step to improve the COD capture in the primary sludge. This way, we can increase the COD capture from 40% to 60% in the primary sludge, and that leaves only 18% of COD requires aeration for removal. And that means we're now able to recover about 43% of the incoming COD as methane. That's 10% increase compared to the conventional practice. But the even better approach will be to completely redesign our treatment system and directly use the mainstream anaerobic treatment for methane recovery. That means only 6% of the COD requires aeration for removal, and this will allow us to recover about 73% of COD as biogas. So benefit of this type of mainstream anaerobic treatment is very clear. So these are well-established process and mature technologies that we can use and have low operation cost, generate less sludge, and do not really require oxygen. However, the mainstream anaerobic treatment is not very widely adopted in Australia. So there are some important practical considerations. For instance, from the technical perspective, one concern is that anaerobic treatment can become less stable at lower temperature conditions. Another challenge is about the footprint. Conventional AD system, anaerobic digestion system, typically require larger reactor size, and because of the slow methanogenesis process that would require longer hydraulic retention time. And there are some other factors. For instance, most existing treatment plants are already designed as an aerobic treatment system, so retrofitting them into anaerobic process can be costly, and there are also limited local operation experience and training available that can all impact the level of adoption. So in the past years, my research team has demonstrated successful high-rate anaerobic treatment of municipal wastewater, even under lower temperature conditions, as compared to those experienced in Australia. So, for instance, in this slide, we show a UASB digester system operated at the pilot scale in the Netherlands. So this is in collaboration with my Dutch colleagues at the Wageningen University. So in this setup, low temperature municipal wastewater is firstly treated in the low temperature UASB reactor, and the sludge from the UASB reactor is then recirculated into a small heated mesophilic digester. And with this design, we were able to achieve stable operation with wastewater temperature as low as 10 degrees Celsius. And the hydraulic retention time was only 6 hours. We also developed a more simplified system configuration, just as a single UASB reactor. So these reactors were operated at a full-scale sewage treatment plant in Canada. So in this setup, UASB reactors were amended with granular activated carbon, and the reactors were fed with raw municipal sewage with temperature ranging between 12 and 18 degrees. As what we can see in here in the performance graph, we were able to achieve a short hydraulic retention time of just 8 to 12 hours while maintaining stable COD removal and consistent methane production. So in terms of the footprint, this type of high-rate anaerobic system can be comparable to the conventional aerobic systems. And therefore, the takeaway message in here is really that the low temperature during the winter conditions is not a technical barrier, certainly not in Australia. So this approach should be considered as a viable option for future wastewater management. This brings us to our third pillar, building climate resilience and community value. So let's take a step back and look at the broader infrastructure challenges we're facing. So we've been focusing on the treatment facilities. They're critical, but they should not be the only focus for us to discuss about. So in water and wastewater industry, pipes in the ground are our biggest asset. They account for over 80% of the total infrastructure value. In Australia, as in North America, most of these pipes are already at or beyond their design life, and they are extremely difficult and expensive to replace. So with the aging water infrastructure, our annual capital expenditure is expected to exceed 9 billion in Australia. And we're still looking at an 80 billion funding gap just to maintain our existing system. But here's the real issue. So it's not just about the aging infrastructure. It's our reliance on the centralized buried infrastructure that actually locks us into this cycle of very costly upgrades and replacement. So this is a strategic moment. So the question is really, do we want to keep investing in infrastructure we know will fail again in 50 to 70 years' time? Or should we start redesigning our system that are more flexible and less dependent on the long-distance underground pipes? So one obvious option is to use decentralized system. This helps us to eliminate long-distance collection system. This will also allow for localized energy, nutrient, and material recovery and water reuse within the same community. There has been lots of studies on the cost and environmental impacts of this centralized and decentralized systems, which has already shown that decentralized treatment systems can offer real advantage. Back to you, Dave.
So I'll quickly run through a couple of examples of decentralized and resilient solutions that are in progress or have been done. One of those, courtesy of Southeast Water in Melbourne, is the Aqua Revo housing development, where they have approaching 460 homes that are using up to 70% less drinking water by using the rainwater harvested in rainwater tanks, reusing the Class A recycled water from their site for laundry and gardening purposes as well. And all underpinned by real-time monitoring and control to make sure that those systems are working well. Another example is by using urban wetlands that have often historically just been there for retention or detention, to actually use these wetlands as treatment systems, decentralized sources of water to be able to supply to their local community. We've got a project that we are working with a bunch of collaborators that is looking at one particular wetland called Troops Creek in Melbourne, It's using real-time monitoring and control to control the flow, and so sedimentation rate levels, to make sure that the natural species that are there are not being drowned or drying out, and also sufficient time for the nutrients, the carbon, the contaminants to be treated. Together then with the plan to put a small package treatment plant on the end to be able to supply, once again, Class A recycled water into the local homes. Yang, back to you.
This is an example of a two-pipe system design to separately collect and treat household black water, which is a toilet wastewater with food waste residue separately from gray water. The source diverted black water contains most of the organic energy in domestic wastewater, as well as over 90% of the nutrients. So this is a very concentrated wastewater and a very good source for energy and nutrient recovery. Gray water can then be used for heat recovery and can be treated for different water reuse options. This type of source diverted resource recovery systems can lead to 80% of water saving, as well as significant energy and nutrient recovery. My team has been focusing on developing treatment processes for source-diverted black water and gray water treatment. This slide shows one of the processes we developed specifically for black water resource recovery. So we use a USB reactor, and by controlling the feeding and operation conditions, we're able to create a localized biochemical environment within the reactor. This leads to localized pH increase and calcium complexation, triggering the calcium phosphate precipitation directly in the bioreactor. This type of process can achieve high ammonia loading rates and biomethane production, as well as recovering 80% of phosphorus as part of the granular sludge, which can then be harvested and used as fertilizer. We've received financial support for a proposed demonstration of black water resource recovery system for a community of 1,700 residents in Canada. For developing this type of decentralized wastewater treatment systems, I want to emphasize that technological innovation is very critical, but equally important is the community engagement and shared decision-making and trust building. So this graph highlights some of the key elements of the trust building, which involves things like trust in water quality, clear communication, and transparency in information sharing. In order to support all this, we'll need to have a very strong digital foundation that enable water transparency, the data transparency, smart monitoring, and inform the decision-making across all levels. And with all that, I will again hand over to David.
So one example of how we are continuing to build trust and transparency using digital technology, water utilities are making this move from this linear asset-based utility, from pipes, dams, pumps, structures, to having now a digital infrastructure where they're going from sensors and devices at the edge through telco platforms, into their own IoT platforms, data analysis platforms, then integrating into their various customer and operational systems, creating a much more customer accessible, community supporting, much more transparent water utility for their customers. One of the examples is how they're embracing a digital or smart metering, primarily for water, but it's also for recycled water as well. There's more data being collected half hour rather than the usual quarterly meter readings, and more data available and more analytics on that to be able to inform customers when they might be experiencing abnormally high levels of usage, potentially leaks, and continuous flows in their homes. So this is an example, credit to Southeast Water and how they are rolling out the process of digital water meters. So in particular, supporting their customers to save money, but also saving water and leading to much more resilient communities. Another example of digital technologies enabling more trust of water utilities are, again, courtesy of Southeast Water, sewer monitoring devices that can be placed because of their low cost in a large number of manholes, really enabling early detection of even pre-blockages. Those restrictions that might lead into blockages means that costs for clearing those and cleaning are cheaper, certainly much cheaper than the cost of cleaning up a spill, but that transparency to communities that they're not spilling into their environment and creating disruption for their environment as well. Yang, I will hand back to you.
I would like to share a major initiative we're leading at QUT, the IoT for Water Hub. This is a 5-year program jointly funded by the Australian Research Council and over 30 industry partners. We're also in collaboration with researchers from 6 other Australian universities. Together with our partners, we've developed a shared vision for the hub, which is to build an IoT system for real-time monitoring and control that supports our water future. We aim to achieve this by increasing water source diversity, enhancing environment and ecosystems, and engaging our communities. Our work is organized around 4 technical areas, including smart and low-cost, low-power sensors, real-time network visibility and decision-making tools, advanced analytics and predictive modeling, and real-time asset monitoring and control. And beyond the technical work, we'll also be addressing other areas like policy, business models, and industry training aspects to ensure that innovation translates into the real-world impact. Over to you, David.
And now it's my privilege to wrap it all up and make sure that you've taken something away out of today's presentation. We've given you a lot of slides and a lot of content, but we wanted to try and show to you our vision for, and the vision of many others in this space that we work with too, and credit and thanks to those that have contributed their input and their slides to this presentation today. Want to show this is the journey that we can see for sustainable water and wastewater operations in Australia. Really, those 3 take-home messages are the 3 steps that we outlined along the way. The traditional approach is not for the future. It's not for the long term. We need to embrace low carbon and low emissions technology and processes for towards climate change. Also, too, we need to make sure that our operations are focused on resource recovery and participating in the circular economy. And in doing that, we are establishing trust. We're transparent with our digital technologies and tools, and being adaptive and really working to make sure we have more resilient communities, resilient systems in the face of climate change, population growth, urbanization, and the aging infrastructure that we have. Thanks so much for the opportunity on behalf of myself and Yang and others that have contributed. Thank you so much.
Thank you very much, Dr. David Bergman and Dr. Yang Liu, for your very informative input. It's now your turn to get involved. Please ask our speakers questions via the chat box, and who your question is also directed to. Thank you for everyone, too, who submitted questions while registering. So my first question is from Vagesh in New South Wales, and this one's directed to you, Yang. What process improvements can be implemented optimizing our sewer treatment plants, improving treated water quality for reuse, and reduce energy consumption?
Oh, it's a very good question. So when we talk about reuse, I guess when we talk about thinking about how we can have like the most cost-effective and energy-efficient system, the most important is to think about the goal for the reuse. So for instance, if we want to produce water for reuse for irrigation purpose versus for direct or indirect potable reuse, the level of treatment should be different. So it's all about fit for purpose. So when we design treatment systems, it's also very important that we think about the treatment performance, the reliability of the system, at the same time looking at the energy use and the greenhouse gas emission as example. So it's all about finding the right balance when we think about reuse. I think another point normally about reuse is about the performance assurance. So when we select the system, a lot of times it's usually about how we can make sure that the treated water meets the reuse requirements and the system is conducting or performing how it should be. So this monitoring system is very critical and often determines the success of the reuse program.
Thank you very much, Yang. My next question is now for David, and this question is from Don in New South Wales. So Don asks, how does the Council's current infrastructure program incorporate sustainability principles, particularly in achieving long-term water security and climate resilience for the community?
Well, thanks, Don, for the question. I'll excuse me. I'll put my own interpretation on that and make an assumption there when he's talking about a council's infrastructure program. I'm assuming a council to be a local government authority that has water infrastructure as part of their remit. And I think in terms of a council really adopting and embracing, future sustainable water management, there's a couple of things that really need to come into play, or observations I've made, those that are succeeding. It really is at that leadership or strategy of vision area. Has the council or the utility really set a vision around net zero carbon, and is that particularly ambitious? So, for example, I saw a presentation recently from Urban Utilities based out of Brisbane, who've set a target not just for net zero carbon, but for net zero nutrients. They want to make sure that their nitrogen and phosphorus is net zero out of their treatment plants. And by setting that vision, it then drives into the organisation the necessary plans that need to come about to deliver that. The second element I think really comes into, has got a lot to do with the particularly strategy and planning teams that are in place and the processes that they follow. Are they looking far enough out in terms of planning around asset replacement when it comes to water and wastewater treatment? Are they looking wide enough in terms of the technology that they should be embracing? And do their procurement processes really allow for innovation and new technology to be considered and incorporated? It can happen that in some procurement processes, anything new is considered risky and is taken out of procurement. We've got to find ways that innovation is encouraged and is actually embraced and proven through part of the procurement and then commissioning and ultimate operations process.
Beautiful. Thank you very much, David. I like the idea of net zero nutrients. That's very insightful. I've got another question for you, and this is from Angela in Victoria. And it's, is circular economy a consideration of a sustainable water future?
Yes, thank you. And I think there's another circular economy question later on that is about how do we make it common practice. So I might bundle those two together, actually. So I think Angela might have posted this before the presentation, and hopefully you've seen through the presentation that resource recovery and the circular economy is a key part of a future sustainable water future. So the waste that is taken at the end of our treatment process, we can see that as waste. But really, hopefully you've seen out of this, there's carbon, there's nutrients, there's energy to be taken from that, and it's a constant stream that's just going to keep coming at us all the time. It has minimal seasonality to it as well. So it is definitely part of a future water solution. How do we make it common practice? Yes, that is starting to happen in a number of places, and there's a couple of things that are driving that. One is the economics of it, and just the realities of a particular situation. So, in some parts of Australia where we're looking at biosolids or sludge treatment, sending it to landfill has either been prohibited, or the cost of doing it is just too much. And also to the acknowledgement that some emerging contaminants like PFAS and heavy metals and others are present in that biosolid. So the traditional approach of sending it to land is actually not a reality and is actually environmentally a problem. So considering both those cost and environmental drivers, we are seeing solutions like pyrolysis and other thermal treatment processes that are destroying those contaminants, creating a biochar that is of potential commercial value. So, and to then enter into the circular economy and be reused. So in some situations, we are seeing that happen. Also to emissions target, net zero as well. Greenhouse gas emissions is driving a lot of participation in the circular economy. And I think you saw in some of Yang's slides in particular about nitrogen removal, nitrogen recovery. It's a great way of ensuring that we're reducing or eliminating the potential for nitrous oxide emissions as well. Greenhouse gas, 300 times more potent as well. So with those kind of targets and strategies in mind, that is also isn't just about reducing those emissions, but it's by participating in the circular economy are reducing those emissions as well. Back to you.
Thank you, David. I've got a question now for you both, and we'll start off with Yang and then move to you, David, for this question. So it's from David in New South Wales, and the question is, what controls do we have for PFAS and microplastics in treated wastewater?
Okay, yeah, so definitely like PFAS and microplastics are basically two major emerging issues in wastewater treatment, and some PFAS compounds apparently have already been detected in our drinking water supplies. I guess in terms of the control, right now the sewage treatment plants are still a critical barrier before these contaminants reach our water and water basically surface waterways. But the reality is that we all know that the conventional systems are not designed for treating the emerging contaminants. We know that some of the compounds can be removed, like including some microplastics, and certain level of PFAS can be removed to some extent from the sewage treatment systems, but majority of the PFAS in particular, they are very concentrated, very resistant towards biodegradation. So the level of removal is very limited. So now if we think about some other control options, there are lots of research and development right now looking at how to potentially remove or treat PFAS from wastewater. Some technology, for instance, like foam, there's foam DAF system. So it's a dissolved air flotation system that has been shown to be basically effective for both PFAS and microplastics removal. There are other technologies like absorption-based processes, membrane filtration systems. There could be very useful, and then advanced oxidation, for instance, can be quite effective for PFAS removal as well. But the bottom line is really to, when we select the technologies, more about where and how we want to apply different type of technology, and then we need to look at the cost and the energy inputs of those different processes. I guess with PFAS, one of the key issues is really around how we can make sure that we are not transferring our PFAS issue from one form to the other. So if we're talking about absorption, you are not only looking at we're removing the PFAS from the liquid phase. We also have that adsorbent that we need to deal with. And when we look at membrane filtration, for instance, we have that concentrate we have to consider. So it's when we look at the cause, it has to be more a holistic type of approach to consider for the process selection.
Maybe if I just add to that, Yang, you've answered that very well. I might just add a couple short things. I think there's still more work required, but we are growing in this space to make sure that we have robust analytical methods for identifying the many, I think the counts up to thousands of potential PFAS compounds that are present, and having analytical methods that we can trust around that, so we can actually know where the issues are and where to focus. The other one is, and this is difficult, but there is work going on in this space, and there needs to be more, just understanding source control. So PFAS, microplastic, other contaminants that are coming at a water utility in their wastewater treatment process is actually really tracking back to the source and then working with the source of those, controlling at the source where possible with more targeted and specific strategies to them, rather than trying to deal with it at a centralized location where it's much more diluted. Concentration is difficult in that space. Also, just in terms of a lot of those contaminants, microplastics was mentioned here as well, typically does process, they end up in the solids component. And this is where the emerging space of thermal treatment is seeming to be increasing evidence showing that materials like pyrolysis under the right conditions, PFAS, is certainly broken down, if not completely destroyed and eliminated. There is more research required to fully validate that, but that seems to be turning out or appearing to be an effective control, that high temperature processing, as well as producing material of value. Thank you.
Thanks very much, Yang and Dave, for covering something that's so important, controls for PFAS and microplastics in detail. I've got another question from New South Wales. This one's from Sebastian, and this one's for you, Yang. So what are some modern technology innovation treatments that are sustainable, and what is blocking these from implementation?
Okay. So in terms of technology that are sustainable, I guess as we just introduced in our presentation, I think one area to consider is, of course, resource recovery. If we have the right community or the right application for the products, then the resource recovery-based system normally can be considered more sustainable. But then if we look at the energy inputs aspect, normally just in general, the physicochemical-based processes are not as energy efficient as biological systems. So they could be biological-based systems normally are a bit more sustainable. And another area we haven't really touched much on, like during our presentation, is on nature-based solutions. We can, if they are designed right, then they could be considered more sustainable. And there could be lots of benefits, for instance, for wetland type of systems. They have the benefit not only for in terms of the treatment, there's also biodiversity type of benefits to a community. So in terms of the implementation, that's a very big question. I guess I can give an example based on our previous experience for developing more decentralized treatment systems and resource recovery based systems. So for a lot of the decentralized system, as example, that with or without resource recovery, they could be considered as more sustainable, but there are lots of challenges. And I guess one of the challenges we learned previously is really about really the range of stakeholders needs to be engaged during that process. So it's oftentimes the stakeholder has to be we have to go beyond the traditional water utilities. So for instance, if we have a decentralized system or like a wetlands in a community, and then we're dealing with not only potentially the utility, it could be councils, it could be body corporate in terms of design or the ownership of the wetland, and then then we need to look at who is responsible for operating this type of systems and for maintaining the systems and paying for the upgrades. So there are lots of considerations to juggle around. Another thing about the newer system is around the regulatory requirements. So a lot of times, no matter if it's a health department or environmental protection agency, we're talking about looking at the longer term performance data and the quality or the performance assurance. Then the longer term operation data oftentimes is not available, and that can really delay the whole process for implementation. And another aspect will be something that we already touched on during our presentation, is around the community engagement, that for the community to actually accept and they're willing to adopt new systems. That's involves, of course, the community engagement, and there's lots of trust building process needed as well. So those all require time, and therefore it's very important for any of the new technologies, more sustainable systems for implementation. It's very important to engage all the stakeholders early on in order for the process to be more successful for the final implementation.
Thank you very much, Yang. I've got a question here from Trevor or Spike, and it's for you, David. So it's with regards to a diagram that you presented for a solution, and he was wondering, with it appearing to him a bit centralized, and I was wondering, did you consider a distributed solution?
Yeah, thanks, Trevor. And I think Trevor might have put that question in fairly early in the presentation, as hopefully later in the presentation, Trevor would have seen it, particularly in the adaptable, resilient communities part of the presentation. Yang and I put forward quite a few slides of decentralized solutions. Certainly, they are part of the future of a sustainable water management. Many parts of Australia, there's plenty of rain available where it falls, yet we often still take our water from quite remote catchments a long way away. So there is, in many cases, plenty of water around. The cost of shifting and transporting that water around, or moving the wastewater around, the pumping systems that go with it, not to mention the embedded carbon in building those systems. Certainly what we'd like to see as we look at growth are these smaller decentralized solutions considered. So you saw the Aqua Revo state as a potential model going forward. Take the algae solution for wastewater treatment. Does seem to lend itself more to smaller regional, perhaps even remote communities on that kind of scale, giving them the quality of water at a reasonable value capital solution as well. So absolutely, Trevor. Decentralized solutions are definitely a part of the future water solution.
Thank you very much, David. I've got a question now for Yang, and it's from Alice B, who's interested in what the best options are for high solids content wastewater treatment in a factory with limited space for treatment, a very specific scenario.
Okay, thank you for the question, Alice. I guess I have to clarify a bit more before I can give better answer. But in terms of the high solid wastewater treatment, so it really depends on the type of solids you have in the wastewater. So if it's organics versus, or if it's inorganic, then you probably want the system to be designed differently. So for organics, for instance, for the high rate anaerobic treatment like USB type of system could be very feasible. And of course, you need to also consider, if it's a biological system that we want to use, then you also need to consider other potential inhibitors in your system in the wastewater. And if it's inorganics, then I will go for more of dewatering type of process. And in terms of the process design, I will think about the type of resources, potential resources you can recover from this process.
Beautiful. Thank you very much, Yang. I've got one more question for each of you as time's running a bit short. I'm sure we could talk about this for another hour if we would like to. But just keeping the sense of time, we've got a question from Sar Alvin Carpo, and this is for you, Yang. And so it's, I believe it's a statement actually, maybe it's something we could comment about or visit. So anoxic zone agitation and aeration air contribution can affect both ammonia and nitrate. As observed in wastewater, these two parameters indirectly, when one is low, the other is high and vice versa. Did you want to talk a little bit more to this one?
Oh, sure. I agree. Yeah, I guess it's a statement. Yeah, so yes, anoxic zone aeration is recently, in the past few years, has been started to become popular, and especially with some of the systems is more permanent, like to have aerated zone in the anoxic zone, so like ABR type of process. Often the ABR, the membrane is incorporated as part of the anoxic zone. And that's mainly when we need to improve the ammonia removal. And of course, that any type of addition of in this type of anoxic zone may inhibit or reduce the activities or like the effectiveness for the nitrate reduction process. So there's always a trade-off. Yeah, so I definitely agree with you. And but the whole idea is really to start to think about how we can design our system to reduce the overall energy use. So potentially like shortcut nitrification for mainstream could be a good direction to think a bit more and put more efforts in. But yes, so the nitrate and ammonia, this balance is always an important consideration for us to design systems.
Thank you very much for your perspective there, Yang. I've got the last question here for you, David, and it's from John Cayley. Why is recycled water for non-drinking much more expensive than recycled water for drinking?
Yeah, great question, John, and well spotted. That slide wasn't up for long, so you've read that one very fast. Yeah, great point. The cost of recycled water for non-drinking purposes, you would think, oh, that's much less, lower treatment levels into agriculture or irrigation. Surely that would be cheaper to produce. And look, the WASA report looked at real project scenarios, real examples. And so this is actually a blend of a range of projects where low cost projects, low treatment cost projects like agriculture and irrigation were included. So on those alone, it would have been cheaper. But when you actually factor in projects where it is supplied into an existing network, where often an additional third pipe or a new network needs to be added. So by the time you build in the cost of adding an additional network into an urban environment, for example, that's when those costs of those projects and the cost of that water becomes more costly than if you were just to be supplying it down an existing drinking water pipeline that you haven't had to duplicate. So hopefully I've made sense there.
Absolutely, David. Thank you very much for that, and thank you to everybody who's listened in and provided some great questions. So that's all we have time for today. Please join me once again in thanking Dr. Yang Liu and Dr. David Bergman for their time and input. I would also like to thank Engineers Australia's industry partner, Queensland University of Technology, for their support. If you don't mind, please complete a short feedback form, which is linked in the description box below to help us improve and plan future sessions. Thank you again for joining us, and we hope to see you at our next Industry Partners event.